Okay, here we are for some Chapter 8 lecture notes. So I have the lecture note outline here for Chapter 8, but I just want to point out available on your Moodle page is a separate document that goes into some of the details on writing Lewis structures. I would highly recommend you print that out. Maybe read through it. I'm going to be referring back to what's listed in this document as we go through some of the examples here for writing Lewis structures. So it would be a really good thing to either have pulled up on your computer where you can kind of jump to it while you're watching the videos, or if you can print out a copy, to have it to refer to, because the basis of how we're going to go about the process of writing these structures, drawing molecules, is in this handout. There's also some other things in there that I'll be referring to. If I can scroll a little bit here. Some other things I'll be referring to as we go through some of the details that'll pop up as we're talking about Lewis structures. Okay, let me go back to the kind of normal view here. All right, so the primary topic, or at least what I have listed here as the primary topic for Chapter 8, is chemical bonding. But the way we're going to be, at least initially, thinking about bonding is in terms of drawing a molecular structure. And we're drawing the structure with the intent to kind of get a grasp on how does the bonding work in these particular molecules. How do the electrons hold everything together? What can we determine about maybe some of the reactivity or the physical properties of the molecule based on the way the atoms are connected, where the electrons are, where maybe there's a conglomeration of electrons on one side of a molecule that's negative, a lack of electrons on the other side that's positive, that will kind of play into the physical properties of the material. So the first page here is kind of a bullet list sort of some of the issues that will pop up. If you look on the second and third pages of the note outline handouts, it's just a bunch of molecular formulas, right? So each one we're going to go through and draw the structure. Some of those will highlight some of the issues listed here on the first page, right? And some of them will just be additional practice. So there'll be some back and forth here. I'm going to define a few of the things here on the front page, but occasionally we'll get into the structures and I'll jump back to some of the issues listed on this page, right? The drawing structures handout is listed here as well, right? But since I want you to already have that as we go through, that's why I brought it up here at the beginning. Okay, the first thing that we need to kind of wrap our heads around here is the idea of valence electrons. So in the past chapter, we did talk about electron configurations and drawing out electron configurations. And just as an example, let me start with a fairly simple one, and let's just say lithium. For simplistic purposes, the electron configuration of lithium is 1s2, 2s1. But what we need to think about in terms of our evaluation of bonding and how we draw a structure is that not all the electrons for every element are going to be electrons that are used for bonding. So valence electrons is kind of focusing in on the electrons that are available for bonding. So in the case of lithium, the complete shells, so any complete energy level, and for our purposes at this point, we're going to say complete as we fill the S and the P sublevels. Anything that's full, those electrons are part of that atom, but they do not participate in the bonding for that atom. So in the case of lithium, the electrons in the 1s sublevel here, we would call core electrons. And it's only the electrons in the outermost energy shell, or energy level, for lithium, this would be the 2s, that would qualify as valence electrons. Right? Now what this will give us is the ability to look at the periodic table and identify how many valence electrons an atom will have that it can use for bonding. So if I pull out the periodic table, right, we said all the elements here in the first column, their electron configuration ends with XS1. So X being that highest energy level, and it's 1s1, 2s1, 3s1 for the final electron that goes in there. That's the only valence electron in each of those elements. So we would say, everybody here, these elements, atoms have one valence electron to use for bonding, right? And if you've got a reasonable grasp on electron configurations, you can maybe see the trend already. Second column here, this would be 2s2, 3s2, 4s2. These all have 2 valence electrons to use for bonding. Right? If we jump over here into the p block, right? Boron, aluminum, right? Boron would be 2s1, 2p1. There are 3 electrons in that highest shell that is being filled. So this entire column, column 13, we could think about those elements having 3 valence electrons. 4 here for carbon silicon, 3 for 4 for carbon silicon, 5 for nitrogen, phosphorus, arsenic, 6 for oxygen, sulfur, selenium, tellurium, 7 fluorine, chlorine, bromine, iodine, astatine, right? And when we get over here, right, it's a little different for helium because it's a little different to fill the first energy level. Helium has 2, but neon, argon, krypton, xenon, radon in the S and P parts of that highest energy level have 8, right? Now, things get more complicated in the transition metals. Transition metals are not something we'll talk about in the first year of chemistry. You kind of come back here and look at how do d orbitals affect bonding and interactions in a higher level chemistry class, usually inorganic chemistry class you might take as a junior or senior. So for our evaluation of bonding, we're pretty much ignoring the d electrons and the f electrons. And if we get down here into the lanthanides or actinides, we're going to forget about the f electrons as well. So in terms of valence electrons, we just need the s and the p. But if you can find the column that an element is in, you should know how many valence electrons it has. And since you always have the periodic table, that should not be anything that stands in the way of getting a good structure for your molecules. Okay, so that's valence electrons. The second thing we want to think about here is what's called a Lewis symbol. So Lewis was a scientist who kind of developed some of the techniques we use here in trying to get our idea of bonding by drawing the structure. A Lewis symbol is a symbol of an element that represents how many valence electrons it has. So we said lithium has 1 valence electron. The Lewis symbol for lithium would be the lithium symbol, and then there would be a dot there to represent the electron. Now, looking across the periodic table, right, the number of valence electrons went up to 8, right? So if we just go across our row there of lithium, beryllium has 2 valence electrons. Now, with 2, what we will usually do is draw them separately. So you might draw one to the right, one to the top. There's kind of 4 areas around a symbol. There's top, bottom, right, and left. Up to 4 electrons, we want to keep the electrons separate. Now, that'll make a little more sense when we start to talk about bonding, right? Now, beryllium is a metal, although it has some non-metallic properties as well. It can have that kind of semi-metal characteristic sometimes. But the idea here is beryllium can interact with 2 different other things. So if it's a metal, it has the ability to interact with 2 different anions. Boron would have 3 for its symbol, right? As would anybody underneath boron if we're writing them in terms of a Lewis symbol, right? And carbon would have 4. Now we're going to draw them all separately for carbon, right? And we will see when we start to look at how carbon interacts with other elements, it's going to tend to make 4 bonds because each of those electrons can participate in a bond. Now, when we get to nitrogen, right, we said there's only really kind of 4 areas around the symbol. For nitrogen, we have to pair up a couple of electrons. And it doesn't matter where you put the pair. It could be the top, could be the bottom, could be the left, could be the right. They're all just representing what's going on around the atom. We're going to preference one particular position or another. But right, this goes back to how many orbitals the element has to hold electrons. Right? There's 1s and there's 3p. Once we get to 5 electrons, we're pairing up electrons somewhere in that particular atom. So there's a pair of electrons represented there, right? And then the other 3 are kind of alone in orbital. But as we continue across, oxygen would have 6 valence electrons. So we'd have 2 pairs, but then we'd have 2 kind of lone unpaired electrons. Fluorine would have 3 pairs, right? And then there's 1 more. And again, it doesn't matter where the lone one is. Could be to the right, could be to the left, could be under. Right? When we get over to the noble gas or inert gas, neon has 8 So we can draw all 8 around there, right? And if we jump up to the next element, sodium, we're back to the other side of the periodic table. So now our valence electrons are coming from the 3rd energy level instead of the 2nd. Okay, so we could draw a little picture of what every element might look like just with the electrons it has available for bonding. Right now, that's helpful to think about, not particularly useful for drawing a structure. That's kind of a very simplistic way of looking at elements, but something we need to think about. So we'll come back in the next video and we'll pick up with kind of a little review of using this kind of pictorial representation to think about what we have already discussed about ionic bonding, and then we'll work our way into kind of more complicated bonding that we see in covalent compounds or molecular compounds.